In this video, we look at the different techniques that you can use to get information from a graph. There's three techniques that we can use. The first one is just reading from the graph. The second one is using the gradient of that graph. And the third one is using the area underneath the graph. When do I just read something from the graph? Now that is when one of the variables on the graph is the variable that they're asking us. The second thing is the gradient. For gradient, we always do y-axis divided by x-axis. So let's take an example. If they ask you to draw a graph of energy used in a resistor versus time. Now, if we look at energy and time, and we're working with a resistor, so R is a constant, you can work with any of the equations that's got both the energy and the time in there. Now, if they tell us they're in a circuit, we assume that everything in that circuit is going to stay the same. The current through that resistor and the potential over that resistor, we're going to take that as a constant. And we're working with a resistor, so R is a constant. So both of them are going to show you that the energy is directly proportional to the time. And that's why we got a straight line through the origin. Now that we have the graph, we can look at the gradient of the graph. And that gradient is always y-axis, which is now our energy, divided by the x-axis, which is time. And that gives us rate of energy used. And you should know that that is power. You have this equation P equals W over delta T on your information sheet as well. The last thing you can do is use the area underneath the graph. When you want to know which variable is represented by that area underneath the graph, we are going to multiply the variables of the x and the y axis. Now let's look at this example. They draw a graph of the current through an ohmic resistor versus the potential difference over the resistor. So there we will use R equals V over I, or if you prefer, you can write it down as V equals I times R, which makes it easy to see if we're using an resistor. That makes R a constant, and immediately that V is directly proportional to I. So the potential difference over the resistor will be directly proportional to the current through the resistor. And that's why we get a straight line through the origin here. And now we want to know what is represented by the area underneath that graph. So on this axis, we've got I. On that axis, we've got V. If you multiply them, I times V, that gives you power. So the area underneath this graph represents the power. Right, let's apply this. They tell us that a net force is exerted on an object and that object accelerates. So here we have the net force and we have accelerate. Draw a sketch graph of that net force on an object versus the acceleration. Now that means I have to put F net on the y-axis, and that will be in Newton, and I have to put the acceleration on the x-axis, meters per second square. The equation I'm going to use is definitely F net is equal to m times a, and since they're telling me I'm working with an object, m is going to be my constant. And then I can see that F net is going to be directly proportional to A. So this is going to be a straight line through the origin. Now in the second question, they ask us to draw a sketch graph, but this time it is from acceleration versus net force. So now acceleration is on our y-axis and the net force is on our x-axis. Once again, they're directly proportional, so that will still be a straight line through the origin. In the first one, they ask us, what does the gradient of that graph represent? Now remember, in that graph, when we look at the gradient, that will be F net divided by A. And the moment that you go and look at your equation, F net divided by A will be equal to m, and that is equal to m. So here the gradient represents the mass of that object. In the second one, we also want to know what that gradient represents. And now that gradient is A divided by F net. If we want A divided by F net, that is going to be equal to 1 over M. So this time the gradient is going to be the inverse of the mass. In the next one, they tell us that a beam of light enters a medium from air. So here we have a beam of light that enters a medium from the air. A beam that enters a medium from air will experience refraction towards the normal. And now we want to draw graphs. Now here we have the angle of incidence and the angle of refraction over there. In the first question, they ask us to draw a sketch graph for the medium of sine theta I versus sine theta R. Now we're looking at Snell's law. The refractive index of the air times the sine of that angle of incidence is going to be the refractive index of the medium times sine of that refractive angle. And since we're working from air, that n is going to be equal to 1, and that n is going to have a constant value because we're using the same medium with the same refractive index the whole time. So if they are both constant, then you will see that sine theta I is now directly proportional to sine theta R. Now, if they ask us to draw a sketch graph for the medium with sine theta I versus sine theta R, it means I have to put sine theta I on this side and sine theta R on this side, and that will be a straight line through the origin. In the second one, they ask us to draw a sketch graph, but now for sine theta R versus sine theta I. Now the relationship is still directly proportional, so this is also going to be a straight line through the origin. Now in the first one, they ask us for the gradient of that graph, and here the gradient is y-axis, which is now sine theta I divided by sine theta R. Now let's go back to our equation. If you look at that equation, and we want sine theta I divided by sine theta R, so that is just going to be equal to the refractive index of my medium. When we look at the gradient in the second one, that gradient is now sine theta R divided by sine theta I. If I want sine theta R divided by sine theta I will have to take that refractive index to the other side, but then it will be underneath the line. And then we end up with 1 over NR. So even though they both have the same relationship between the two variables on the axis, the gradients are different. Now in this question, they tell us that an isolated sphere is negatively charged by adding extra electrons. And now they tell us the graph represents the magnitude of the charge on the sphere versus the number of electrons. Now we need an equation. Now, depending on your information sheet, you will either have n equals q over qe or q equals n times qe. Same equation, just written differently. This is the total charge on the object, or the total charge of all the electrons altogether, and that is the number of electrons times the charge on one electron. And remember, the charge on one electron, that is going to be a constant value. So the moment that you look at that one, you will see the charge is going to be directly proportional to the number of electrons, and that's why we have a straight line through the origin. And here they ask us, what does the gradient represent? Now here the gradient of that line is going to be q divided by n. So if we look at this equation, q divided by n, that will just be equal to the charge of 1 electron. Now they ask us to calculate the value of x. So one way to do this is to substitute into my equation the value of q over there, 2, and that axis is in nanocoulomb. Now remember, in this equation, you can either leave out the minus signs on both sides, or you can add them on both sides, because on this side it shows that the charge of that electron is negative, and it means the total charge that will be given to that sphere is going to be a negative. And then you end up with x being 1,25 times 10 to the 10 electrons.